And this type of problem is very important for two basic reasons. One of them is, of course, that it is the difference in composition between a liquid phase, say, and a vapor phase at equilibrium that is the basis for many of the important separation processes that we have. Distillation, gas absorption, gas stripping, and a number of others. But the other reason is one that I mentioned yesterday, and that is that it is the basis, more often than not, that we have some access to being able to evaluate activity coefficients in non-ideal liquid solutions. So we have those two reasons. So let's get started with it. The reading for this, I've indicated here, I've also posted that. But the first task we have in this is to properly specify a vapor-liquid equilibrium problem. And what that means is to know how many variables are going to be required to fix the intensive state of the system. And you've seen this, I think, before. It's answered by what we know of as the Gibbs phase rule. So our task is we want to find what we call F here, capital script F, and that's equal to the number of variables, if I can abbreviate here a bit, required to fix the intensive state of a system of P phases and C components. And we get at that by considering the phases as separate entities. First of all, let's say I've got some phases here, but they're not in contact with one another. And the phase rule tells us how many variables are going to be required to fix the state of each of these as independent phases. And that's going to be, of course, for each one of them, the temperature and pressure and the mole fractions, and we'll need C minus one of them. So as independent phases, we require, then what is it going to be here? I have C minus one mole fractions plus a temperature in each and a pressure in each, so I'm going to require a total of, what, E times C plus 1. That makes sense? But these phases are presumed to be in mutual equilibrium. So we have a number of equilibrium relationships. And we can start to count them. They all have to be at the same temperature to be in thermal equilibrium, and that's going to be P minus 1 equations. They all have to be at the same pressure. It's going to be another P minus 1 equations. And if they're going to be in equilibrium, then they have to have the same values of fugacities of all of the components in all of these phases, so that's going to be C times P minus 1 to give us a grand total of the number of relationships here equal to, if I can put this up, C plus 2 times P minus 1. Oops. So I'll get F here by looking at this grand total and subtract from it the number of equilibrium relationships. And that works out to C minus B plus 2, as you all know. So the statement that the number of variables required to fix the intensive state of the system is equal to C minus V plus 2 is what we know of as the Gibbs phase rule. Now, there's an important assumption that we've made in this that has been tacit, and that is that every component has access to every phase. So if one or more of the components was insoluble in one or more of the phases, I would need to subtract that from the number of equations required and the number of variables required, so Gibbs phase rule will be modified accordingly. But if that's the only issue, then those two factors balance each other out. So I should be okay with this phase rule. Yeah.
This is assuming no reactions.
Yeah, and it also is assuming no chemical reactions. If I have a chemical reaction, let's say I have R chemical reactions, I would have to subtract from C that number of reactions because it reduces the number of independent components. We're not going to encounter that, but that's a good point.
Why does it matter that they're not that one phase might not be soluble in another? What changes? What of our derivation?
Well, we
what
get
changes?
one y less, right? We get a y. One of the y's is less, but then we also have a relationship which is less, so they balance each other out.
I mean, one of the y's doesn't necessarily have to be less. Each y is associated with each individual phase,
Well,
right?
let's say that one of the components is insoluble in one of the phases.
Mm-hmm.
So in that phase, it doesn't have a y. So that reduces the number of variables by one, but it also reduces the number of equilibrium equations. And those two factors balance themselves out.
Okay.
Okay, let's move ahead then to looking at one of these problems. So what we've got is a vapor liquid equilibrium system. As I've sketched here, the whole system here consists of two phases. So phi is equal to 2. It has a liquid phase and a vapor phase. And it has a temperature and a pressure. And there will be an appropriate number of mole fractions in the vapor phase and the liquid phase. And I'm assuming that all the components are present in both of the phases. So for this situation, the one that we're interested in, we're going to have C minus B plus 2, but B is itself 2. So the variance here, or the number of free variables required, is just equal to the number of components that we have. So if we look at the total variables that are used to describe the system, that's going to be what? Well, I've got C minus 1 mole fractions in the vapor phase, I've got C minus 1 mole fractions in the liquid phase, but I've got a temperature and a pressure. So that means the grand total number of variables is 2C. But I need to specify C of them to fix the problem. So that kind of sets up the format for us. We're going to have C variables that are fixed to fix the state of the system, and then C unknowns that we can presumably solve for. Now, the actual problem can be in a number of different formats, but I'm going to list here the most typical ones that we have and then make some comments about that. So let's say that we're given, this is a typical one, all of the mole fractions in the liquid phase. That's my notation for that. I'm going to make these squiggly brackets. And temperature, and then be asked to calculate the system pressure and the vapor phase composition. Another type of problem we might have is to be given the liquid phase composition and the pressure, and be asked to determine the temperature vapor phase composition, then of course I have to permute it and get two more types. I may be given the vapor phase composition and the temperature, and be asked to find the pressure and the liquid phase composition. And lastly, be given vapor phase composition and the pressure, and be asked to find the system temperature and the liquid phase composition. Now I might have, this covers about probably 90+% of all the problems that you would encounter in vapor-liquid equilibrium, but we can have other cases. For example, I might have both the temperature and the pressure specified, or I might have neither one of them specified and have the problem specified in terms of just compositional variables alone. Those are other kinds of types of problems that we'll look at one or two of those later on, but for now, this covers the major